The field theory can be combined with the thermodynamics with the binary temperatures, especially in the early universe. For the phase transition, such as thermal field theory or binary temperatures field theory is applied. And continuing the effective potential with the zero temperatures, we can give the T dependence term in the potential. So reviews on the effective potential, we can derive this from the effective reaction. This is the generating functional and the generating functional, and we can define the effective reaction capital gammas with the Legendre transformation. And by dividing the three-dimensional spatial volume and the time, we can obtain the effective potential. This can be evaluated by the path integral formulation, but there is also other way by using the series expansion. The coefficient of this series correspond to the 1pi endpoint correlation function. This is because the end derivatives of the effective actions becomes a 1pi endpoint correlation function. And by the Fourier transformation of the this endpoint correlation function, and by using the some prime form in the Fourier transformation and the Dirac deltas, which comes from the momentums and energy conservation, we can obtain the effective actions as the following form in terms of the endpoint correlation functions with the powers of the scalar field. For example, if we consider the following scalar potential, there's a possible endpoint correlation functions at 2.4 point, such even numbers of the external legs. And if we consider the one loop, then the endpoint correlation functions has the following form. This is the end power of the propagators, including the vertex, from the Cortic self-interaction terms of the scalar field, and some combinatoric factors, and the diagram reflection double counting is multiplied here. Then the one loop effective potential has the following form, because according to this formula. And then also this can be obtained by the path integral formulation, and then by using the identity of the logarithm functions, series expansion, and after the oblique rotation to the Euclidean space, we can obtain the one loop effective potential in the zero temperatures, and the insides of the log terms can be rewritten with the effective mass, which is the quadratic coefficients of the potential. So here is our final result for the zero temperatures. Also, this can be obtained by the path integral formulation by using the background field method, so that the fluctuated fast oscillating field is integrated out, and the effective action can be directly calculated with the Gaussian integral and using the determinant of the quadratic matrix. Also, both this can be applied to the complex scalar spin 1/2 fermion field with the kappa matrix, and the Gazy boson, the spin 1 field, by considering the propagators with the matrix and the degrees of freedom. And also this can be developed the higher order loop, but here's the we only consider the one loop order, and there some cutoff regularization or dimensional regularization for loop diagram will be applied, and such regularizes give some specific scale. So if we apply for the standard model case, then the contribution comes from the Higgs, Corti coupling, WZ gauge boson mass, and among the fermion, only the top nuclear coupling contributes because it is the dominant one than the other fermion. Already this is discussed in the previous videos for the effective actions and effective potential. So after the dimensional regularization, the renormalization conditions gives some specific scale in the logarithm, and by adding the counter term we can remove the divergence and neglecting the constant. The important term is this one. The 1/64 pi scale represents the loop effect, and the m4 powers is the effective mass, and in the inside of the logarithm there is effective mass scales over the renormalization scale and b scale. So this gives the zero temperatures one loop effective potentials already we discussed. So this is now the new part, the thermal field theory, by considering the effects of the temperatures. From the statistical physics, the probability density is given by the Boltzmann factor exponential minus beta h over the partition function. Here the beta is 1/the kt, and in the quantum statistic, the expectation or the observable can be obtained by the trace of the multiplications of the observable operators capital O and the probability density law. Similarly, we can obtain the endpoint correlation function or green functions by considering the observable expectations of the ant field multiplication, similarly for the 1pi endpoint correlation functions. And for each field, this is given by the field quantizations of the quantum field theory, and for the Hamiltonian insights of the probability density, this is also written by the creations and annihilation of the operators in the field quantization formalism. So the important ones is inside of this multiplications of the n field and the expectations with the probability density contains many ladders of right A, daggers, and A. So the expectation values of the A, daggers, A with the normal ordering is very important. So this is the probability density functions, and if we consider twice of the A, daggers, A's, and the probability density functions, then by using the identities of the series 6 functions, then this expectations of the A, dagger, A gives the Boltzmann statistic number density. Similarly, if we consider A dagger, we can obtain the similar one plus the MB. So for the 2-point correlation function, the propagated this yield the following form, and MB is a Boltzmann statistic as 1/the exponential betas e minus 1. So this contains the thermal effect with the temperature dependence. And there's important identities in this thermal field theory. If we consider the time-going propagators by considering the pi at the t and x and the pi at the 0 and 0, and if we insert the t minus I betas instead of the t by considering the imaginary time formulation and using the identities of the twice and changes the order. This is the same with the G at the t-axis with the time going to the past. So the correlation function show that the periodicity with the Bates as the 1 over the t by using the imaginary time formulation. And by using the Fourier transformation, the propagator in the momentum and the energy space, there is the imaginary time, the periodicity, and the energy is the quantized by this periodicity for the boson case and the fermion case. Similar to the quantum field theory, by using the contour integral, we can obtain the full form of the propagators in the energy momentum space by using the residue theorems over the complex plane. And this gives how we can deal with the propagators and the loop integral and the vortex in the thermal field theory. The propagators are given by such a form in the energy momentum space. Omega n is quantized by such a form, so the betas includes the time process effect. And the loop integrals over the momentum space includes the 1 over the betas, also the additional factors with the temperature dependence term. So, and for the one loop effective potential reminds that this is given by the inverse of the propagator. So if we replace the form, the loop integral has additional 1 over the betas factors, and these terms are replaced by the quantized energy. So now the betas thermal effects are included in the one loop effective potential. And we want to integrate this term by using some techniques and identity. We start the function v omegas and differentiate this function, and using identity, the v omegas can be rewritten in the analytical form. And so the one loop effective potential with temperature dependence term can be written like that. And the important one is the temperature dependent part, the binary term. So if we define some function jb of the y square inside of this one as this form, and if we set the omega case as p square around case, the relativistic energy momentum relation, then the one loop thermal potential can be written with the function the jb with the of the m scales of the disk. Here the m scales effective mass comes from the potential, and the thermal effects are included in here, like as capital T, the temperature one. Also similarly, we can do that with the fermion. So the result of the one loop thermal potential is given by such a form. This is a boson contribution, this is a fermion contribution with the degrees of freedom. For the small mass, the high temperatures, the JB and JF function can be expanded order by order. This includes the log term, and for the boson term there is the cubic terms in here. So inside of that, the y is equal to the m squared through the t square. So this gives the t 4 times the m over the t cubic term. So this gives the t times the pi cubic term. Such a pi cubic term from the bosonic contributions gives important law for the phase transitions in the early universe. So we can set the thermal potentials with the polynomial form, with the quadratic term, cubic term, and the quartic term, and the coefficients of each term can be evaluated in terms of the WZ gauge boson mass and the Higgs boson mass and the Topcock mass. And in the standard model, such a cubic term is small due to the large Higgs mass. So the burst or the phase transition is hard to occur. So today we discuss the thermal field theory as an overall review, starting from the effective potential and considering how we can deal with the propagated and loop integrals with the thermal effect, and there are bosoning and the Brownian contribution which gives the phase transitions in the early universe. In the next videos as a series of this, I will discuss the strong order phase transitions one more times again. Already we discussed this in the Lacterowick baryogenesis video.